because we're going to try really hard to be customer oriented and make sure that you get what you need if we can. Okay, with that, I'm going to start first by taking a breath. All right, so let's talk about how residential water is used. This is going to be a presentation on how fixtures influence water use and how occupancy influences water use. This is unapologetically nerdy. I appreciate all of you who are interested in this sort of intimate details of each fixture's water consumption. But I'm going to show you it's super important. I would not waste your time if it wasn't important. So the first body of data comes from these research sites. We've been monitoring them since 2014 or 15, and all the data I'm about to show you is at least 1 year's worth of data, if not more. These are all electric apartment complexes built in 2014 and 15. They're LEED Platinum. They're zero net energy efforts, which means some of them succeeded, some of them didn't, but they're close. Now, I apologize for those of you who've seen this data before. I promise we'll be digging into new stuff, but this is such a big insight. Note first that the little X boxes go in a very nice, even, so these are like averages essentially. You can see them at the middle of these boxes. One's a mean, one's a median. So anyway, close to the same idea. In the middle of each of these boxes, you'll find the average spot. And the average only goes up by 1 kilowatt hour a day per occupant. So the first occupant uses about 13 kilowatt hours for themselves in their apartment, their all electric apartment, and you add another person, it only goes up to 14, and you add another person, it only goes up to 15. The range of consumption stays pretty wide. Note that the one person occupant has a huge range from 5 up to 20, 21, with a couple outliers. That range of 15 kilowatt hours, if you go, say, down to 2 people, you stay down at 5, but now you go up to 27. These are big ranges, always there, at least a 3-fold range, if not a 4-fold range from the lowest to the highest. And that's what one of the things I'd like everyone to understand is that with identical incomes and identical apartments done to the identical standards, everyone has the same, we know how many people live there, etc. There's a 3- to 4-fold difference between consumption in these identical circumstances. People are very different. This is important for understanding how water use happens because people are very different. This is an example of the electric loads averaged over a year, and we're looking at a 24-hour period. So this is the average day for, I think, all 88 tanks that we had monitored. You can see in dark blue the average line for the 1-bedrooms, which has a mixture of people, 1 to 2. The red line, which is the 2-bedrooms, which is going to be 3 to up to 5 people. And then the green, which is 3 bedrooms, which is going to be in the range of 4 to 7 people, but usually about 5. Focusing in on the same type of table, but looking at just the domestic hot water demand now. So drilling in. I think I should slow down a little bit because I'm talking myself out. Okay, so this is just water heater demand. Yes, and this, as Jim is saying, this is electricity, not, and this is important because a lot of this electricity you're looking at now is resistance backup, as opposed to the heat pump. That explains, for instance, what happens when you go from a 1-person household to a 2-person household. This 1 to 2-person household jump there, that's the kick-in of a large amount of electric resistance because people are now taking 2 or 3 showers in a row, which is what will trigger electric resistance, whereas a 1-person household will not. Let's see, there's a question here. Nick Peterson's asking, what is the state of California doing to provide incentives for going all electric linked to sustainably generated electricity, also for solar? Seems like incentives are mainly funneling through utilities and not directly to the consumer. What's happening to state incentives to rooftop solar? Is there a need to start state initiatives to address this? Just briefly here, the state incentives have pretty much dried up for new construction market rate, and there's tons of money now going into affordable housing. And since about 40% of Californians would deserve to live in affordable housing, and the solar funds are even available to apartments that are not technically affordable housing, but have poor people, so to speak, living in them, low-income folks. So that's the new reality, is yes, there's been somewhat of a diminishment of funds, but it's going to the right places. Previously, the solar funds were going towards wealthy people who arguably didn't need it. And the other part would say is that the incentives have done their job sort of globally. Now the price of solar panels, when incentives started, you could buy a solar panel for $5 a watt. Now you can buy it for 15 cents a watt. That is a difference from 2005 to now. So $5 to 15 cents. We have incredibly cheap solar, and the price hasn't even stopped dropping. Okay, back to water. Here we have, what's interesting to see is also it's pretty flat. Once you get to 2 people, these lines, these averages don't go very far. Now, this is all masked by the electric resistance. So I want you to see what this is, the hybrid total energy use, which has a lot of issues dealing with the programming and the fact that resistance is there. Not all water heaters have it. Okay, now you probably absorbed what you can see here on how electricity is being used by hybrid water heaters. And I want to say that this issue has not changed. Our 2018-2019 data, which I'm not showing, but it illustrates the same issue, a lot of electric resistance kicking in. There we go. When I say electric resistance kicking in, this is what that looks like. On top, we have 1 occupant. On the bottom, we have 5 occupants. There's a different scale on the left. Note on the 1 occupant, the compressor is staying at about 80 watts. And then there's some static, some electric resistance here and there, but not much. Just a little bit in the morning, around 8 o'clock, but not really. I mean, there's obviously some around 16 o'clock, which is 4 o'clock in the afternoon it starts up. Now, going down to 5 occupants, there's a different scale on the left. We couldn't fit it onto the page if we had the same scale. Now, the compressor is at 150 watts, so about twice as much. And the electric resistance, note that it starts kicking in at 4 in the morning, maybe 3:30. People assume that, well, let me put this differently. There's a lot of people who are low income who work shifts. Like about 1/3 of them work at night, do night shifts, and frequently are working the jobs that require them to get up earlier and get to places, even if they're working a day job. It's an early day job. It might be construction, it might be agricultural work, but sort of dawn kind of work. So this is these big bumps of electric resistance might be an hour forward if there's a different economic stratum, but the pattern itself holds well. So large amounts of electric resistance kicking in. So I asked this question, I'm like, well, what if all of that electric resistance heat, which we're going to assume was needed, like it got the tank back up to 125 degrees Fahrenheit. So one way or another, we needed a tank at 125. But what if that was all compressor energy, not electric resistance anywhere? So we were reflecting more of the energy pattern of a Sandin, for instance, the CO2 heat pump that doesn't have electric resistance, or my heat pump, which is a freebie I got from a company called Viken over in China. No electric resistance, just a bigger compressor. I could go on. There's other products like that. So I wanted to know what if it was compressor only energy, and this is what I got. If all the energy is now just the heat pump energy, starting at 1, 2, 3, 4, 5, 6, 7, this is the energy demand with 50-gallon tanks uniformly, every single tank. So it's a very gentle increase. Okay, so this is an insight now that we can see a very pure pattern of how occupancy changes the energy demanded for water heating. What's neat and interesting and is going to be revealed further as we talk more through this presentation is that the increase is small, it's slight, it's subtle, it's not significant. I mean, there is a large jump. I mean, you can see it goes from, say, 2.1 for one occupant to 2 to 3.4 for two people. That's a large jump, right? There is an increase, but it smooths out, and it's not a doubling. Like, two people use less than one person. Three people, the per capita rule that we'd seen previously still holds, where there's something about sharing a home. There's lots of things I should say about sharing a home that allow people to share hot water, with the exception of showering, which is a very strong, but not perfect, but a strong linkage to each person takes their own shower, basically, but not completely. there's also evidence that maybe not everyone shares. Some people share showers. Okay. This electric resistance issue, this is a problem. And Jim says, did I divide the resistance kilowatts by the COP? Yes. You can see there's two COP lines there. So if we assumed a COP of 3, this is the red dotted line. If we assumed a COP of 2.4, there's our dotted line. So we wanted to show, sort of error bars and get a sense of sensitivity. So this is a COP sensitivity analysis. So we can see that the bands of possible energy there. Because of course the product works at different COPs in different seasons and with different installations. Some are in garages, some are in closets, some are on the roof, that kind of thing. So there was a range of installation places for these tanks, but we were able to get a nice clean set of data from it. Note the R squared is 0.43. What that means is that while there is a line to be drawn, it is not fair to think, well, you can just see the dots. The dots represent the real data. The dots are real. The line is imaginary. The line predicts an average, but the dots are how the real world works. And the dots show you that the world is highly variable. Look at the spread on the 1 bedrooms. Look at the spread on 2s and 4s. It's big. Let's see here. Next, I'm going to go into, okay, trying to suss out what is going on with electric resistance backup is important, because these yellow dots represent electric resistance water heaters, the electric resistance part of it, of the hybrid water heater, in a different way. This is an EPRI study. And the EPRI Electric Power Research Institute, what they're documenting in this subdivision with 9 homes is that the biggest peak loads are the electric resistance elements of the water heaters, the hybrid heat pump water heaters. You can see other peak loads like the cooling loads starting in hour 4320. So this is 8,760 hours in a year that are being mapped, all the hours of the year. So starting in the spring heating season is these blue dots that are showing up a whole bunch in the middle. That's the peak air conditioning load, which everyone is very aware is a problem. That's the summertime loads. It can lead to brownouts in different areas, just with electricity supply. But look how, it swamps it as a problem. It's a huge problem. The electric resistance kicking in is a huge grid problem. This cannot go forward. We cannot succeed in electrification if we have to assume that there's these peak loads that are 3 and 4 times larger than the peak air conditioning load. They're happening during the summer and the winter time. It's more in the wintertime, but there's plenty of this where you look at the air conditioning peak loads, peak electrical draws, and the water heater on the same day is doing something twice or three times or four times as bad. So knowing this is a real problem, and we need to really deal with it. Get nerdy, go into the details, find technical solutions. Don't let this continue. Um, this sort of sets the stage for the next part of this presentation, where I'm going to explain why we started studying water heaters, hot water demand, in such granular detail. This is the fundamental argument here. This is a grid look at what the problem of not understanding water heater demands creates, with a clumsy tool called electric resistance backup that's like a hammer into the grid. Really not gentle what's going on there with those peak demands. Okay. Back in the day, about 8 years ago, when I started digging into this question, I went to Jonah Shine at the EPA, who was a technical lead for the WaterSense program. And I was asking, saying, look, I'm trying to design zero net energy homes. I need efficiency measures to be counted, specifically efficiency measures like low flow shower heads and thermostatic valves for the shower heads and more compact structuring of our water demands. And I had a whole list of things that I wanted to be able to capture the efficiency. That I knew the efficiency was real, but the modeling software that California had and has did not reflect of like a tightening down on the water use, not even from going like a 3.0 gallon per minute shower head down to 1.5. There's just nothing. You were stuck. And on top of that, the water use consumption predictions were inaccurate to apartments. The structure of predicting was a square footage allocation. It said basically, there's going to be 23 gallons or 26 gallons of hot water used no matter who lives there, and all the water that's used after that, we're going to guess by using a square footage metric. This amount of water, whatever is 0.17 or something, some small amount of additional hot water per square foot. But single family homes are very low occupancy compared to multifamily. And starting in 2008, California started building a majority of their housing as apartments, multifamily. So come 2012, I was looking at the situation thinking, I am working on the majority of the housing and I am using a tool that predicts single family hot water consumption as opposed to say the doubly occupied apartments that I'm working with. It might be literally twice as many people per square foot. And I don't have water running all over this building. These are small apartments. They should get credit for structural savings if it's possible. I had all these ideas where I'm like, this doesn't really work. It doesn't work for me as an efficiency person, doesn't work for zero net energy design, just doesn't work. There has to be some other solution. And so Jonah Shine directed me towards this body of research. In 1999, on the left, was published The Residential End Uses of Water. I think it was about 1,200 or 1,100 homes in which they put up acoustic sensors and they listened to the pipes and they documented what it sounds like. What's the pressure wave, essentially, that comes through the pipe when you flush a toilet versus when you use a shower. And they were able to identify about 90% of all of the stuff going on. The faucets, they couldn't easily figure out the faucets, although they did eventually analyze and say, we think the faucets divide out where 2/3 is kitchen sink and 1/3 is bathroom sink, which helps, when you're looking at fixture efficiencies to think, where's the possibilities with fixtures. Put out there, not great possibilities because people don't use faucets full blast anyway, and they only use them for a second. About half of the loads are just 1 second long. So showers, I'm going to say this again. Look at your shower heads. The second report, Residential End Uses of Water, had about 700 as opposed to 1,100 and change, about 700 houses that they studied. But it was the same group, it was the same tools, it was extremely standardized, their methodology just got better, you know, but it didn't change in an important way. And so these are the two largest studies done in North America or the Europe side of Eurasia. And I don't have access to science really over in China and Japan, not much. Kenji, you know, if you know of research like this that's been done in Japan, I would love to learn it. But I did research like what was being used in Europe. And so I talked with researchers over there, read their papers and such, and felt like uh, they were stuck in some of the similar problems. Okay, thank you, Jim, for correcting me. He says the reuse studies are based on the existing whole house water meters, not acoustic. Well, maybe Jim, you could clarify what's the tool, because I believe that they did, you know, they were able to parse out what uses we're going through. But I'll let you put that on the chat. But anyway, methodological question aside, which is still important. Here's the methodology here on the side of what towns were looked at. We had them across the United States, mostly cities that were interested already in water efficiency. So like Waterloo, Ontario up in Canada, that's kind of neat because they have an engineering college there that really specializes in hot water. Waterloo is sort of an area of expertise in Canada. Okay, moving on though. You see a whole cross section, hot climates, cold climates, etc. Now this is the kind of data that they published. And what can we learn from this? You know, there are things to see here. I'm dissatisfied, right? But I want to at least, you know, give them credit here for these are some, I give them tons of credit actually. They did tons more work than this, but this way of looking at it, where you have an average household, an average, like say 2.7 people in that household. This is what you'd see for an average household. I mean, they took all their data and averaged it. The red is hot water use, the blue is cold. You can see that the clothes washer, for instance, is a large user of water, but it's mostly cold water. You can see faucets there, which is like 55% hot water. Actually, pardon me, I think the red is a quantity of the blue. That's what's going on, my bad. So you're seeing red is the subset of the blue, which is mixed water. So now moving across, you can see clothes washer, faucet, leaks are significant, and that's true in both studies. Leaks are significant use of water, and showers. And they have other. Leaks are not the same as other. There's other things. There's like hot tubs, for instance, that are other, or humidifiers that are other. Leaks, truly, as best they could tell, were leaks. Okay, so if you were to draw a line, once again, through a wide band of data, look how big the bands are. They're almost as large in every single household. Like the one person household looks like they have almost as wide of a range of consumption as a 4 or a 6. Just one person, everyone's different. People are so different in the way that they consume energy and water in their households. It is profound. An individual person, you know, this is encapsulating the whole range of all the friends and family and strangers you've met in your life. People, all these people are in these houses. And you can see at one glance that individual people are different in their behaviors. So, but I want you to see the weakness of predicting any one person's demand by drawing an average line. The averages are not strongly clustered around, people's behavior is not strongly clustered around the average. So, okay, looking at this data, the researchers at Peter Mayer very kindly opened up access to their entire big data set. And Lauren Adaby, one of my staff from a few years back, 2015, she went in and did big data grabs using, I can't remember if it was R or Python, but one of those big data grab organizing software programs where you can go into massive amounts of data and get graphs out of it. So I asked her to graph with the whole mixed, so it's mixed water use. This is not hot water use. This is mixed water use for how showers behave by occupancy. Having identified that occupancy was the single largest, best predictor of, not like square footage, for instance, occupancy really is the best way to predict how much water is being used in a household, unsurprisingly. So there's 4 different ways of drawing a line through these black dots, which are the real data. And the phrase power fit, where the line bends, that consistently is the best predictor. It's not, I won't say completely consistently, but pretty much consistently, like excepting leaks, for instance, which seem to be just based upon having a house. You'll have leaks at about the same rate as anybody else. And leaks are mostly catastrophic. Like 85% of the leaks are, I think it's only 85% of the volume, or there's it's a whole other study to talk about leaks. I'm going to garble it. Most leaks are, there's a small amount of leaks that are the majority of the volume of leaks. And it's mostly toilets. So leaving aside leaks for the moment, showers, you see a power fit, a curved line starting from left to the right, going from 1, 2, 3 up to 7 people, where it was the occupancies that we had. And keep in mind that 6 and 7 people are uncommon sizes of households, so the data is strongest with smaller households. 1, 2, 3, 4 occupancy households, very large amounts of data. 5, 6, 7 in declining amounts. That's important for a little bit later to understand, because look at how this power fit line touches on the top, touches the 3 and 4 and 5 occupancy households. So 2 people with a kid, 2 people with 2 kids, or 1 person with 3 kids, you know, those households, the average household in the United States is about 2.7 people. So there's a problem here that I identified once I put all of these, I thought, the best lines for predicting each of these fixtures together. There's a problem with showers, is that this line, which has a 96.96 R squared value, which means it's extremely accurate to the data, very good fit to it, but it's not fitting the 3 and the 4s and the 5s. It's under predicting them, which matters when it's the single largest use of hot water, that the most common household sizes, or not the most, but some of the most common household sizes are not getting the best prediction. You know, maybe we're doing a good job of fitting 6 and 7 person households, but they barely exist. So this has, the formula is y equals 12.92 x raised to the factor of 0.82. And I'll show you later, I actually raised that to like a 0.84 to get accuracy to 2, 3, and 4 bedroom households. A little bit to sacrifice it though for 1 bedrooms and 5s and 6, 7s. 1, 6, and 7s lose a little bit, but 2, 3s, and 3, 4s, and 5s particularly benefit from this work. Okay, still with me, fellow nerd folks? Great. Okay, let's look at the second largest use of hot water, faucets. Here, I want to point out that I had the same problem and I had to adopt the same solution. So the 2, 3 size households and the 5 person households are not being accurately reflected in that. So I also increased the exponent a tiny bit. I'll show you that in a moment. But note that it's a different line. I just want you to see that the increase in showers is steeper than the increase with faucets. They're not the same increase per capita. And this is a big insight. These are the 2 largest uses of hot water. They're also not used in the same way over the course of the day, which I'll show you in a moment. But to capture this is that these are different uses of water. They might as well be, you could think of it as like, what if we had a water heater for every single appliance instead of sharing it? But what if we had like an electric resistance water heater underneath the sink and next to the shower and such? Then all of a sudden it would matter that each fixture used water differently, wouldn't it? If you imagine that, do that thought experiment and think, if I use that approach of figuring out what each fixture is using, maybe I'm going to get a better prediction of how the tank gets used or how a central recirculating system would get used, and what would efficiency do to that. These flows, by the way, are like 2.2 gallon per minute shower flows and 1.5 gallon per minute faucets. And these are relatively high flows as opposed to CalGreen, California-based standards, which would be, I think, a 2.0 gallon per minute shower head. And there's tons of 1.5s that people use these days with all sorts of water efficiency programs out of the drought that we had. Lots of parts of the country incentivize 1.5 gallon per minute shower heads. But we have not had a way to predict accurately what that would do. So this is that kind of effort for showers, for faucets, clothes washers, also a power fit. Note the data gets kind of messy when we get up to 5, 6, 7 households. Note the R squared for power fit is a 0.68, reasonably good. There is more accuracy if you use a best third order polynomial fit on the bottom. But I don't trust the data from 5, 6, 7 person households enough to adopt an entirely different graph for it. And it's a mess. Like, I'm not sure what you get out of this effort because the formula turns into this huge polynomial that just sucks. No one can interact with it, even as a researcher. Other people have these polynomials in some of their predictive water use software, and I find it too obscure to even work with. I'm just not a good enough mathematician to use it. So power fit it is, and I do think that it's appropriate to the data. Baths. Not a whole lot of water used in baths, but when it's used, it's a fair amount. So here you see, power fit was once again very accurate. The linear was a little bit more accurate, but once again, it felt like looking at how the whole house water is used as a power fit, how 1999 data, I'm only showing you 2015, power fit seemed to be accurate and consistent. So that's what it was. And yeah, power fit has the benefit of bending a little bit at the top. And I think that baths are shared generally, especially with multi-occupancy households. Kids will share baths, adults will share baths. And so a power fit recognizes better the sharing than a linear. The fact that there's a somewhat decreased water use per capita, that's what a power fit would do. This is how I think about it. Here's leaks. Leaks was so all over the place that we ended up adopting a line on the left that's pretty much just straight, which means like a per capita amount of hot water, as opposed to there being like a power fit that goes up. However, that's what the 1999 data shows us. This has really bugged me, but Peter Mayer, the lead researcher with Dr. D'Orio, he was recommending that we do a per capita. So I believe what we're using then is, on the left-hand side, a power fit. Okay, we're at 9:42, and Amanda's making sure I've got time for questions. Jim, over here on the side, you say, the fit is so good because you're predicting averages. The R squared isn't capturing all the variability that you talked about before. Right. So each of these black dots represents an average, and then we're drawing a line through the averages. So yeah, the data is even more messy than what we're showing here. But I think, Jim, to your point, that maybe if we had a whole huge blur of data on each of these graphs, we might get a slightly different line. than using these averages. That's fair. And that might be the next step to go here. Um, so Nick, I apologize. I'm just answering questions about the water use, but thank you for your thoughts there. So other, which is a whole mixture of things that are other. Uh, I'm using the power fit on the upper left-hand corner, but I did also want to look at what was going on back in 1999 because I just felt like other was such a weird use. So in both, we see an angle going up, a per capita increase. And because the 2015 data is like 60% of the number of households as the 1999 data, which is much larger data set of 1,100 versus about 700 in 2015 data set. I do trust the pattern that the 1999 data found more, especially on things like this, other. So anyway, we did use the 2015 data. We used the power fit, which seemed to be a close match, like it echoes what we saw in 1999, but still using the most current data. Here's toilets. Toilets are very large water use in a household, and of course have no hot water in them, except in cold places where they'll sometimes run hot water to the toilet so the pipes don't freeze. Which, if you've ever experienced this, is weird to sit on a steaming pot of hot water. That's just, I don't recommend it. But none of the data that they had showed that behavior that I've experienced in my life in more than one very cold Wisconsin home. So here you have the power fit for toilets. This is the best line, and there's tons of data on it. It's a good line. Fits it strongly. The fraction of hot water used by each fixture. Now, this insight, look over there on the right-hand side and see how hot water is used by a clothes washer at 20% hot water, showers at 66%, faucets at 57%, leaks at about 12%. Then you have baths, which are 59%, closer to what a faucet is than what a shower is. Interesting. But probably because you're surrounding yourself in hot water versus having it cool when it's flowing through the air before it hits you. So hot water is about 1/3 of the total water, and cold is about 2/3. But that 33% hot water doesn't match anything. No fixture uses water at a 33% level. The closest you have is other, which is a minute use. So the biggies of using hot water, you're looking at an average does not tell you how hot water is going to be used. If you say your clothes washer is a standard clothes washer and it's using like 30 gallons of water in there versus an Energy Star, which uses 14. So you can have a 50% reduction in water use and hot water use at that, and not be able to capture it. So this approach, I think, is important especially for predicting efficiencies, which is why I started this work. Okay, good. Still working here. Now, this is what my calculator looks like. Up on the top in blue are the assumed efficiencies of water. In yellow are the things that I can enter now, and I can say, my shower is not a 2.3, it's a 1.5. And by applying essentially a fractional reduction, saying the difference of 1.5 over 2.3, that percentage, which is something like, I don't know, 60, 70%, that's now a reduction factor. I multiply against the water use. So the line is still the same, but it's down a little bit because there's a water efficiency applied. Down in the bottom here, you can see in red places where I increased the exponent to better match 3, 4, 5 person households, 2, 3, 4, 5s. So from an 8.2 is what the graph showed to an 8.4, and from a 0.56 to a 0.61. That, yeah, I've already explained myself. I'm doing that on purpose to try to do a better job of predicting the average, the most common households. This is what an output looks like for mixed water. There's 24 hours in a day. The water is being used differently in each hour of the day. So we can start getting into that peak impact. So this is for mixed, and this is for hot. Same idea, every hour is a different amount. Every fixture has a different pattern of using it. When you graph this out, on the left you can see for the mixed water, and on the right is the hot water. If you go down to the top line is total, and you can just see that the lines are somewhat different, the way hot water is used versus the total water. But it gets more different when you go to the bottom, where you start seeing the individual uses, their hourly impact. At 7 o'clock, sorry, I have that at 8 o'clock and 8 o'clock. Generally, the two peak hours of the day are the 8s. And so you have toilets being a peak use for all house water, whereas definitely showers that are the peak use in the morning. Big time in blue, with faucets below it. This is what 3 people look like. In the morning now, it's not the toilet that's the #1 use, it's the shower, just in total water volume. And in the evening, you're seeing faucets. Over on the hot water side, it's even more dramatically showers, but the faucet really appears more than it did before. We have slightly different use patterns. We get into 5 people. In the evening on the right-hand side, now it's showers that are the highest use, and faucets are no longer the highest use in the evening. So you have subtly different patterns, and particularly if you want to apply efficiency to this, if I want to drop that just the hot water used by the shower, because I've got a shower retrofit program I'm deploying, this kind of graphing is going to get you an accurate understanding for how water changes, both in peak and, like, if you want to reduce the peak use of hot water, put in a shower or faucets. You understand that the efficiency measures can be measured in both their quantity and in their timing with this approach. Last but not least, my favorite things to approach. So showers being this huge use of hot water, especially peak use of hot water, it's both largest peak and largest total quantity. 1/4 of our showers are wasted water, 2 minutes. Multiple studies over and over have seen this as a 2-minute period of time before people actually use the shower. And of that time, about 40% of that is waiting for the hot water to get there, and about 60% of it is the water is hot. It's like 95 degrees Fahrenheit, and no one's getting in for a minute. So what can we do about getting rid of waste of hot water? This is the best device I think that's out there right now. Is a technical strategy. It's where you put a thermostatic valve in line with the shower, and it shuts off the water once it gets hot, and you just pull on the little tab in order for the water to come. And I've been doing this in my own house now for 12 years. And I've come out with one now that does the same thing for tub spouts, so that when you're evacuating the cold water, once the water's hot, coming through the tub spout at 4 to 6 gallons a minute. So it's a huge amount of wasted water if you're running the water hot from a tub spout. So it just shuts off the tub, and now you have hot water waiting there for you. So that is the conclusion of my tech talk. I think I've managed to keep it on time. We're at 9:52. And I would love it if there were any questions that I could help people out around this presentation. You type it into the chat most easily. Let's see here. And I don't know how to do that whole hand waving thing where I could hypothetically let you speak if you needed to. But, okay. Well, if there aren't any questions at the moment, then I'm going to focus on this for another moment. So this Sunday, Monday, and Tuesday this week, Gary Klein, thank you, Danny. Gary Klein was up here, and he was leading a team. Larry was also here, Larry W. And then my crew. What they were doing was trying to understand this 40% part of it, the 40% of warm-up waste volume. And what they were doing was getting all of the plumbing equipment that's sold in our country, all the copper types, all the PEX types, and they were testing shower head flow rates and the friction inside the pipes as you get to declining dimensions of pipes, going from, say, 1/2 inch to 3/8 inch to 1/4 inch. Um, and what we're trying to do is figure out how skinny of pipes could we have so that, let's say you had a thermostatic valve, because that's a smart idea. Um, well, you could have less piping, therefore have less warm-up waste volume that has to get evacuated from your pipes. And there's cold water sitting there and you have to get rid of that before your hot water arrives. Well, a 3/4 inch pipe has twice as much water sitting in it as a 1/2 inch pipe, which in turn has about twice as much water sitting in it as a 3/8 inch dimension pipe. So we can get rid of about 3/4 of the water that's sitting in a pipe by making it go from 3/4 down to 3/8. And we wanted to know, like, well, that would take this 40% and take 30. It would take 3/4 of that out. That would be remarkable when you're looking at this being the largest peak load and the largest load like that. That's a good chunk. Um, it might be, like 1/10 of the total shower is just this issue around the plumbing being too wide, having too much storage volume in it. So that's the origin of that research for me, is to try to understand how skinny of pipes could we go so people get their hot water faster and there's less waste, just inherent waste to it. And without us having to necessarily cluster all of the uses of hot water in one place, which is the more standard approach right now. We have a code credit. Danny Tam is about to drop off, right, from the Energy Commission. His organization is in charge of a code credit for having all of your hot water uses within about 10 feet, I think, of the tank. That's still assuming 3/4 inch delivery pipes. So there's a certain volume of hot water that's sitting in all those pipes that they're trying to reduce by giving this credit if you accomplish clustered plumbing. This strategy of putting 3/8 inch piping in, that gives us flexibility. That allows people to have, heat it as much as you want. It allows them to have the water heater in the garage and use the interior of the house, as so many designers do, for the residential uses, and not mechanical systems. Architects seem to hate mechanical systems and they always forget about them on purpose, and because they're hoping they'll just go outside. Go in a garage, go in the attic, go away. So in order to accommodate architects' interest in design flexibility, we could put in skinnier pipes. And okay, got 4 minutes. I'm wrapping it up. Just so you know, I'm just sort of riffing here, just giving you my last thoughts. um, yeah, we're studying skinny pipes, thermostatic valves paired with it, so we can get rid of 1/4 of the shower, which is just waste. Larry, you're asking, is there any data that shows the benefit of installation of the hot water pipes versus not? Yes, there's definitely data on that. The impact, I don't have it here to show you, but what you see in the morning time is clustered water uses where people are showering and they're washing dishes and such. And water can stay hot in an insulated pipe for like 45 minutes so that you don't have to waste water by evacuating it. You'll still get tepid or warm water at the tap, for instance, in the morning if someone else took a shower with insulated pipes. Whereas if they're uninsulated, within like 10, 15 minutes, all gone, no more heat. There you go. So quick answer to that. So with that, I'm going to conclude. Thank you all for your attention on this deep dive on how occupants and fixtures use water and how that hopefully will change